certain canonical transformation, okay, we basically have to find out what is the generating function. Sorry, the generating function is given and is given. You basically have to do some transformation so that you can write down that equation, okay. So what we are going to do is we have taken this form, okay. These two parts are given, the generating function is given. I will write it down first in this form, small q and capital Q, which is very easy because what I do is in this term, the small q's are already there, right? Small q's are already there. I have to just replace p, small p. So I can replace this small p in terms of small q and capital Q, and then we'll get whatever is the answer. So that is one transformation that we did. And we also want to find out what is PQP. So for that, we actually has taken help from the generating function formula that we have. That is P is equal to minus del F del Q. And then finally, we just replaced some values, did some standard calculation, and finally arrived at this result. Okay. So this is what we did yesterday. But then here, if you read the question, okay, if you just read the question once, it says that uh, for a certain canonical transformation. So that means that it has already been assumed that this is a canonical transformation. Okay. Or the question already tells you that this is a canonical transformation. But then if there is a function given and I don't know whether it is canonical or not, and I want to find out whether it's canonical or not. Okay. So that is the next part of the lecture. So condition for transformation to be canonical. So now the question is, will this transformation be canonical? Okay. So the condition is this. Look into this now. This is basically a form of an exact differential. Okay. So if this df, which is the generating function, okay, f the generating function is a function of q and p, and if this equation is given by this, that means this df is an exact differential. We can say that the transformation is canonical in nature. Okay, so it might be a bit vague, but then when I discuss the problem, it will be more clear to you. So if df is an exact differential, okay, uh, then if you know if f is a function of q and p, okay, so we are saying that this f is a function of q and p. So if f is a function of q and p, then df can always be written as del f del q dq plus del f del p and dp. Okay, so the question is that if I can find out what is the form of this f so that this entire equation will become an exact differential, okay, we basically are saying that the equation is canonical in nature. Okay, so this is what we are going to do now. So let's just take an example so that it's more clear to you. Okay, the examples will explain it better. So the question is given is this. The question is that they have given you the transformation equations. Okay, q is equal to root over 2q e to the power a cos of p, and capital P is equal to root over 2q e to the power minus a sine of p. Okay, you have to show whether this is a canonical transformation or not. So the transformation equations are already given to you. You have to show whether it is a canonical transformation or not. Okay, so this is a something which is asked. So let's just try to use this logic here. Okay, let's just try to do this. So for doing this, the first step is write down this form. So can we write it down? Okay, let's see. So you see, if you look here again, it is this p dq. It depends from question to question whether you find out dq or you find out this dq, capital dqj or small dqj. Okay, so it depends from question to question which one you exactly want to find it out. Okay, so what we are going to do is take up this capital Q and find out what is dq. So you know it's already written, right? So what is my q? Q is root over 2q e to the power a cos p. Okay, e to the power a cos p. Let's find out the dq of this. Okay, so this is actually simple. Okay, so q is equal to e to the power. Okay, when I forgot to just write it down here so that we can root over 2q e to the power a cos b. Okay, so not e to the power a cos b and root over 2q is there. Okay, so this is what is given to be q. If I want to find out dq of this, if I want to find out dq of this, there are two variables here. One is p, one is q. Okay, so what I will do is I will differentiate it with respect to P and Q. So first let's differentiate with respect to Q, okay? So for this, what we can do is we can keep e to the power a cos of P outside, and then I can take ddq of root over 2q. But then there is no dq as such, so we just multiply it with dq, and then this d and this d is there, right? Because of this. So we have this. In the second part, we can just take root 2q outside, e to the power a outside, and differentiate it with respect to p. So ddp of cos p of dp. Okay. Now everything becomes a bit more simpler. So e to the power a cos p and ddq of root 2q, right? So root 2 is common, can be taken out. Okay. We have to just differentiate ddq of q to the power half. Okay. So if we do that, we can just write it down as nx to the power n minus 1. So half q to the power half minus 1 into dq. Okay. And then ddp of cos p is minus sine p. So there is a minus sign there. And then minus sine p dp. And root over 2q e to the power a. Okay. Once this is done, what we can do is we can just try to simplify this a bit more. So you should keep track of what is being done. Okay. So e to the power a cos p, this root 2, and then there is 2. You check the power. It is half minus 1, which will be minus half. So 2 to the power minus half. And q is also half minus 1. So q to the power minus half dq. Minus e to the power a sine p root 2q into dp. Right? Once this is done, you have a simplified form of dq, capital dq. Okay. So can we just put it to that relation? So what we are going to do now is we are going to put it here. P dq minus small p dq. Okay. So what is my p dq? So what is my p? Just get back to that problem. The p is root 2q e to the power minus a sine p. Okay. So we can just put that value root over 2a e to the power minus a sine p. Okay. And dq we have just now calculated. dq we have just now calculated minus p dq. So what we can do now is this. See this. This is, maybe I can just, this is minus a, this is plus a, this is plus a. So this e to the power a cancels out, right? E to the power a can be taken out, so e to the power a gone. Here we have got 2q to the power half. This is 2q to the power minus half. So the first term won't have any 2q. Only term left out would be cos p dq. So cos p dq, right? Sin p is already there. Sin p is already there. And then what about the second term? Second term we have got root 2q into root 2q. So this will be 2q. Okay. And then we have got sin p dp. Sin p dp. We have this minus of p dq. Okay. Now I think the next step is quite obvious. We'll combine all the dq term, okay. We will combine all the dq term. Here is one dq and here is one more dq together. So it will be sine p cos p dq minus p dq, and then this term will be there. So it will be 2q sine square p dp, right? So we have separated out dq and dp. That should be the final aim, because whatever equation you are writing, see, it says that f is a function of q and p. So the final equation that you are getting should be in terms of q and p. That should be the first aim. Okay. So whenever you are writing down this form, you do the differentiation and write down the equation in terms of p and q. You see, everything is in terms of p and q. Okay. So what we can do now is to know whether it's an exact differential or not. We can just play around a bit. Okay. First thing is this. This is sine of p cos of p. So if I just multiply it with 2, okay, and divide it by 2, we can simply write it down as sine of 2p. So I can write it down as sine of 2p into half, right? Minus of p dq minus 2q sine square p dp. That remains the same. Now, this is the tricky part, okay? What we can do is, can we write down this equation in this form? Del q of the term, okay, what we have here into dq. So if I write down del q of this, I have to multiply 1q here and 1q here. This is the partial differentiation with respect to q only. So if I include a q in this part, this q, and include a q here, and if I take delta q of this entire term, I'll get back this term. So that means this is okay, right? But for an equation to be an exact differential, this part and this part should be same. So right now, if you are not very clear about it, what you can do is we can simply take the same equation, this exact equation, but now differentiate it with respect to p and check whether we get this equation or not. If we get this equation, that means this is an exact differential. Okay. So let's check now. So here it was del q of this equation. Here we are taking del p of the same equation. So what is the answer? So if we take, okay, if we take del p of half q sine 2p minus pq, let's see here, half q can be taken out because we are differentiating with respect to p. Sine 2p can be nothing but cos 2p into 2, okay, minus of q because del p is 1, right? So it is minus of q. So we just take q common inside the bracket, this 2 to get cancelled. It will be cos 2p minus 1 or q, and cos 2p can be written as 1 minus 2 sine square p, okay, from trigonometry, minus 1. Minus 1 gets cancelled. I get minus 2q sine square p. Is it the same term? The answer is yes. See? This is minus 2q sine square. This is the term. So if I differentiate it with respect to p, I still get back this term, right? So that means whether you differentiate it with respect to q, understand this logic important. Whether you differentiate the function with respect to q or with respect to p, the function that is there is the same. So in both the cases, this is the function, this is the function. This is called the idea of exact differential. So you see, this is an exact differential. So if this is an exact differential, it means that this is canonical transformation. Okay? So if this is an exact differential function, okay, exact differential function, we can say that this function, which we have derived from the form of capital Q and capital P that has been given, and we can call this transformation as canonical. This is canonical transformation. Okay. So what did we do? Let's just get back because I think one sum is more than enough to understand what needs to be done. Okay. You will be given a question in terms of capital Q, capital Q, small q, or QP, capital P, everything. Okay. Whatever form it might be given. Finally, the question is you have to show whether this canonical transformation or not. Okay. And the method is called exact differential method. There are different ways of showing it. Okay, we can even show it using Poisson's bracket, but then that we'll do it later. But then if it asks specifically to show whether a transformation is canonical or not using exact differential method, then whatever we have done now, you have to do that. You cannot use a different method. Later on you will see a method which is more easy to do. Okay, but then that will be done later. So how do we start? We start with this equation. We start with this equation. This is the equation that we are going to use. Okay. And in this, we know that there is a dq and d capital Q. Depending on the question, we'll either find out what is small dq or what is capital dq. Okay. So in this particular question, what we did was we found out what was capital dq. We found out what is capital dq. Okay. So we just did the normal differentiation. Okay. And then we put it into the final form here. Okay, and then we got an equation, okay, in terms of dq, in terms of dq and dp. Okay, so every term should be in terms of small p and small q. Okay, once done, we can actually rearrange it in such a way so that if I take ddq or ddp, it should differentiate the same function and give you this result. Okay, so this way we can say that this is basically nothing but an example of exact differential. This is an example of exact differential. Okay? So you see RHS is an exact differential of f, and hence transformation is canonical. So you have to do some kind of modification, calculation, and so on. Okay, so let me just give you this question. Okay, so I'll keep this on screen and I'll ask you, all of you, to please write this down. Question is, show that the transformation, okay, So please write it down, or you can take a screenshot and then start doing it in your copy. Q is given, small p is given, capital P is given, capital Q is given. So more or less, you've given all parameters, okay? But then you have to do it PDQ minus capital PDQ, okay? And then find out the term, okay? You can start with small q, dq, small dq. I'll just give you a hint here. And you have to show that this is canonical using exact differential method, okay? So this is can be taken as a classwork as well as a homework, okay? So you have to solve it, try to solve it, okay? These kind of questions are very common, be it your final exam, mid-sem exam, entrance exam, okay? So you are expected that you solve it very fast, okay? When you're giving for your entrance exam. Gate also, they do ask you these kind of questions, okay? Graphical mechanics. So you have to practice this, okay? So this is on screen, and this is what you have to solve, okay? So try solving it. You have to show that this is canonical using exact differential method. So this is important. Let me just give you for, let's say, 15 minutes for this, okay? So uh, prior to 15 minutes, you will arrive somewhere. At least you will have some idea on how to do it, okay? So the approach is this: small p dq minus capital P dq. Write down that, simplify it, try to find out the exact differential form. So when you have small p, small dq, you can find out what is small dq. And when you have capital P, capital DQ, you can find out what is capital DQ. Now, whether you have to find out D small q or D capital Q depends on the question. Okay. The transformation equation should be that way. Okay. That's very important. So you see in this, capital Q is written in terms of small q and P, but small q is written in terms of capital P and capital Q. Okay. So you can start from small dq. I'll just give you this hint. Okay. Put it there, try to do the transformation and see if you get the exact differential. Okay. So let me just give you 15 minutes for this. Okay. So, sorry. So try doing it. Okay. And then after 15 minutes, I'll ask you. Okay, so I guess you should be able to have some answer with you. Might not be the exact answer that we need, but then I'm sure you have progressed at least somehow, somewhere. So anyone has a form of the generating function, the f value that you have. Okay. See, I'm not going to answer this. Okay, I'm just going to give you probably this as a homework. But then any one of you could do it. I think that will be important. Okay. So if anyone has an answer, just tell. So actually, the ultimate aim is to, of course, you have to show it that it is basically an exact differential. But the ultimate aim is to find out the form of f, okay, form of the generating function. That is what is the most important part here, okay, in these kind of problems. So this is something which you have to do. So maybe as I scroll down with the answer, you can just get a hint. But then I would like you to solve it. Okay, I have also not solved it entirely. I've just written the answer and the hint. Okay, but then you should be able to do it. See, the answer that you should get is this. Okay, you should do your differential equation. See, what I've done is dq. You have to do dq, replace it with p dq minus capital P dq. Try to take it in the exact differential form. Okay, then finally get f. So what's your answer? The answer that you should get is half p sine of 2q. Okay, half p sine of 2q. So look here, this part. Okay, half p sine of 2. Capital P. Okay, not small p. This looks like a small p. This is capital. So this should be the answer that all of you should arrive at. Once you get that, then it's okay. Okay. Please take a note of the next question. I'll give you the next question also, and all of you have to keep trying. Okay. Please keep trying. Very important. Please take a screenshot of this, or if you're writing it down, please write it down. Show that the transformation capital P is equal to small q cot of small p, capital Q is equal to log of sine of small p by small q is canonical. Okay, and it has also told you what is should be the generating function. Okay, so the generating function is this. You can take a screenshot of this and try to solve this.